each one. And I'm indexing from 0, just to make it more explicit. So we start with S, the non-terminal S. We're going to apply the first production rule. So we're going to substitute 1 mod 3 is 1, obviously. So we substitute X with the first production rule. 0 mod 3 is 0. And 2 mod 2 is 0. And we continue down the string until we reach the end, and now we have a string in the language. So now we have the representation, which is grammatical evolution. We solved that problem. The other thing we need is the fitness function. How are we going to measure how good the input is? Remember that problem. So we can observe the program's dynamic behavior. When we put an input in, we can watch what happens with the program and judge how good our input was based on the static control flow graph. We want inputs that maximize code coverage. In other words, inputs that cause previously unobserved behavior. In other words, inputs that go places on the control flow graph previous inputs haven't explored. So what are we going to use for this? We're going to use a statistical model. Statistical models are handy for explaining what we mean by rare or expected or unexpected in a quantifiable way. You would use a statistical model here if you owned the casino to find out, the expected earnings that you would have. Obviously, you wouldn't want a game where it is exceptionally rare that someone loses and they walk away with all your money. So there's a particular type of statistical model called a Markov process that is appropriate in this case. But rather than bore you with theory because it's statistical theory and I think everyone will go to sleep, I'll just try to show you how it works. So during a generation in our genetic algorithm, we keep a running total or sample of the solutions that use each transition in the control flow graph. So that's just from a particular node, how many take one edge versus another. So in this example, you can see I sort of labeled just on this control flow graph lots of probabilities or ratios. To compute the fitness of a particular solution, we calculate its probability. And we're assuming a Markov process. I know only statistical people would even care about that. So let's not go into that. So let's say a particular string follows a path down this control flow graph. A, C, E, D, G, M. Its fitness would be its probability. So all we do is calculate the probability. And all you have to do that is multiply the total number of the total proportion that took that execution path. So in this case, we do that, we get 0.18. So as you can see, the lower the numbers on each edge that you take, so the less that place has been explored, the better your fitness is. So now we have the two things we need. We have a representation, grammatical evolution, and we have a fitness function, the sampled Markov process. So now that we have those two things, we need a specific implementation, and that's what Sean is going to explain.
We're going to go ahead and plug in the laptop so it doesn't die in the middle of the presentation. Hi, everybody. My name's Sean. Thanks for coming to our talk. I'm going to dive into the implementation part. No more theory. So the first thing we need to do for the implementation is to extract the subgraph of the overall control flow graph that includes all the nodes existing on a path between what we're going to choose as our source and our destination. To get the entire control flow graph, we're using IDA. We wrote a little plugin to spit out the control flow graph. And then we're going to squeeze in on it as far as what we're interested, the part we're interested in. One thing to point out is the rejection set. We're going to identify rejection nodes because those are going to become important later on when we want to short-circuit a genome. Once it reaches a point that it can no longer reach the destination, there's no reason to continue executing it. And we have a little image coming up here. So first of all, if we consider a really simple program, very simple, and say this is the control flow graph for it, and these are all the nodes. Say we identify the source, which could be the receive we talked about earlier, and then say we see a vulnerable API call, such as a string copy. The next thing we want to do to trim down the control flow graph is to find all the nodes that are on the path or on any path from that source to the destination. So we did this using a little bit of modified depth first search. So now we see what we're interested in mostly is the path nodes, and those are all the nodes that are reachable from the source on the way to the destination, so we can track progress of the genomes that are in the population. Now another thing we're interested in is going to be the rejection nodes, and you can think of the rejection nodes as sort of a fence around the subgraph that we're really interested in, because if anybody tries to go outside of the fence, we don't care about them anymore. So we're going to get rejection nodes. Basically, the way we did that was just look at the nodes that weren't on a path and then iterate through the nodes that were on a path, and if there's an edge going to that node, it's a rejection node. So now we have a subgraph that we're interested in mostly, which is the source, the destination, all nodes that are on some path from the source to the destination, and then the rejection nodes, which we'll talk about a little later again. So now, what we want to do when we have the graph we're interested in, the subgraph, we're going to place breakpoints on all these node addresses. Sidewinder is going to run the target application inside a debugger. So as it pushes each genome through the execution, when the debugger hits that node address, it's going to pop up and call a little subroutine that's going to do it's going to keep some information about where it's going. So, like I say, the breakpoints are used to evaluate progress. What we do is we'll run the genome through the target application. And as that genome hits nodes that have breakpoints on them, we're going to track it. For each genome, we're going to keep a history, the path history that it's taken through the control flow graph. So as long as it continues to hit nodes that are on path nodes, we're interested in where it's going. So we're going to keep adding those addresses into the path history for that genome. Now, if that genome hits a rejection node, it's no longer capable for the node to reach the destination. There's no path from a reject node back on. So we're no longer interested in keeping track of where it's going. We'll just go ahead and short circuit it and move on to the next genome in the population. And I think that's what it says basically, when destination is determined to no longer be reachable. If we haven't reached the target, we're just going to kill it and go to the next one. And here's a little illustration to continue from the last time. We see the subgraph we're interested in, the source, the destination, the on-path nodes, reject nodes. We're just going to simply place breakpoints on all those. And that's really all we're interested in during the execution. So once we have that subgraph that we're interested in, it's just a matter of running Sidewinder. And just to recap, it's going to start with an initial population of some amount of genomes. It's going to push each genome through the execution, through the control. It's going to execute it through the target application. It's going to track it as it goes. As it hits those nodes, we saw how the fitness, as it hits nodes, it's going to build a history path. And another thing we're also going to do is as those nodes get hit, we're going to keep a visit count. That visit count is what's going to be used to calculate the fitness once we run all the genomes through. So those numbers that we saw, the percentages, 75 took this path, 25 took that path, all that's done while we're actually executing genomes through the application. So once we run them all through, we'll go ahead and calculate the fitness. So for each genome, we'll just look at its path history and just calculate its fitness as it goes along for whatever, how far it made. Once we have that, we're just going to go through, look for the best genomes, the most fit, and then we're going to do the GA. We're going to cross them over and mutate them and build a next population and just continue doing that over and over until, you know, we hit the target destination node or whatever the goal happens to be. So we're going to give you a little demo because those are more fun to watch. We have two little demos, two little target application. One is a key validation, a simple little key validation. It's a little crack me written by Harlequin. Now all it does is take in a 10-digit key, and you press a button and it says yes, the key is valid, or no, it's not. As far as, thank you. I'm going to talk about a few things. I'm going to describe the application before we actually run the demo, so you'll know what's going to happen before it happens. So that's all that target application does is it tells you, yes, you found the key or you didn't. The goals for Sidewinder in this case, we just need Sidewinder to find a valid key. That's all we wanted to do. So we have to pick a source and a target. And this is a very small application. It's written in assembly. So the source is just going to be the node that handles reading in the key from the text box. And we're going to choose the target destination node to be the node that handles popping up a message box. Yes, you hit the node. No, your key's wrong. Now the grammar that's going to be imported for this one consists of terminals that are all printable ASCII. They're lowercase alphabet, uppercase alphabet, 0 through 9, and then some other valid window file name characters. I think there's like 94 characters. So the grammar has 94 terminals, and it's an ASCII grammar. So what it produces is going to go straight into the text box, and we're going to go ahead and press enter and see what happens. So we'll go ahead and pull this one up so we can see what happens. First thing it's going to ask is for the target application, the graph description language, which is the subgraph structure and everything, the grammar, and it's a process in this case. So we see the GUI come up. In the top left, we have some GA settings. It's just for all the theory stuff. What do you want it to do? Refine it. And then we have over here, we have a little, in the bottom left, a log window. The interesting window is that best genome window in the top center. What that's going to do is for each population, after it's done calculating the fitness for each genome, it's going to pop up the top fitness genome in there. Now, if there's multiple genomes with the same fitness, it's going to randomly choose one. You will notice that they'll pop up in black. If you get a red string up in the best genomes, that means that particular genome made it somewhere further in the path. So it's done something good. It's going to be rewarded. It's going to become the top genome, and it's going to get a breed with everybody else, depending on some of the GA settings. If it prints up in blue, that means it made it to the target. So we go ahead and we choose a source node and a destination node, and we're going to see the graph pop up. In this one, we show the graph because it's small enough to put in there. In the next demonstration, there's over 1,000 nodes or so, and we don't have it working with the graph yet. It's like 750 megabyte graph file. So if you look at the graph, you see there's the target, the source that we chose, the destination. Those are all the nodes that are on some path, and that's sort of the control flow. So once we have that, we go ahead and press play, and you're going to notice best genomes popping up right away. As it hits the node, it's going to color it green, so you can kind of track its progress. Now up front, there's just some random stuff happening. The interesting part of